Morning, everybody. So today we're going to get into talking about amines, and we've talked about these off and on throughout the last 2 semesters, but we're really going to focus on the chemistry here that we can see with amines. Up to this point, we've largely been dealing with amines as bases, right? And they're bases because of what? They're lone pair. That's right. They have a lone pair of electrons on the nitrogen atom, right? So amines can function as reasonably good bases in a number of reactions, but since they have a lone pair of electrons, they can also function as nucleophiles. And so we're going to focus an awful lot on the nucleophilic character of the amine functional group in this chapter. So we'll talk a little bit about nomenclature, not a whole lot. You all can figure that out pretty much so on your own. And we're going to talk about the physical and spectroscopic properties, and then talk about some amines that you might know a little something about just from our everyday lives or from history, and then talk a little bit about how we can prepare amines. And there are a variety of ways in which we can prepare the amino functional group. Okay? So we all know that we can have primary, secondary, and tertiary amines, and they are defined by the number of carbon-nitrogen bonds, right? So primary amine will have 1 carbon-nitrogen bond, meaning that it has 2 hydrogens, and so on and so forth. But in all of those cases, we have the lone pair of electrons. We can have 4 bonds to the nitrogen, and it'll take on a positive charge, but we no longer call that an amine. What do we call that? An ammonium salt. That's right. Quaternary ammonium salt, because the nitrogen no longer has the basic functional properties of the lone pair of electrons. Okay? So we've already talked about primary, secondary, and tertiary amines. We're not going to spend a whole lot of time on that. Okay? We know that amines can react as bases and that they can also react as nucleophiles. So for example, if I take an amine and I throw it into an acidic solution, let's say HCl, I'm going to get the ammonium salt out of that particular reaction. If I take a tertiary amine and I throw it into an alkyl halide, for example, so something that has a good leaving group, okay, so here E would be a carbon atom, we can form a new nitrogen electrophile bond and end up with a quaternary ammonium salt as well. Okay, so this is what happens if I take an amine and I place it in, like, let's say methyl iodide. I will get a new carbon-nitrogen bond. And these reactions actually occur pretty well. What kind of reaction is that nucleophilic reaction, if you had to describe it? SN2. It's SN2. That's exactly right. Can we have SN1 reactions? Not in this one we couldn't, right? But in fairness, if we could generate a carbocation, amines would react with a carbocation to form a bond there as well. So yes, we can form bonds by both the SN1 and SN2 pathways. Having said that, amines like to do the SN2 pathway. Okay. What is the difference between nitrogen functioning as a nucleophile and nitrogen functioning as a base? If I look at those arrows, how they're pushed, they look identical to me. What's the difference? Why don't we call the top one a SN2 reaction? Because of what it's attacking, that's right. So when a nucleophile attacks a hydrogen or a proton, right, we're talking about acid-base chemistry. When it attacks a carbon atom or some other atom other than hydrogen, then we're talking about it behaving as a nucleophile. Okay? So real quick, I want you to show me a method for making that quaternary ammonium salt. And there's more than one correct answer. this is what we've got to make up here, right? So we're going to have to make a nitrogen-carbon bond of some form. Which carbon-nitrogen bond do we want to form? Okay. So let's say we want to make this bond. So we could take trimethylamine and react it with what? Why would I need bromine? Yeah, but what's X here? Does it have to be halogen? Do we have a halogen up here? So you're saying just do that? I can just buy a bottle of that? No. But what can I do? I can take that tosylate, right? Tosylates are good leaving groups. I can do the SN2 chemistry. Tosylate is the leaving group, and I end up with that tosyl salt, right? Whatever this group is tells me what my leaving group had to be, right? So I knew that I had to start with a tosylate. Is that the only way to get to that product? How else could I get to that product? What do you think, Harrison? Is that the only carbon-nitrogen bond that I could go after to make? What other one could I do? That's worth full credit. There's another one up there that'd be just as equally worth full credit on an exam. Say it. So pick one. All right. They're all the same. It doesn't matter. But it's to a carbon methyl group or a nitrogen methyl group, right? So I could take this amine and I could react it with methyl tosylate. I can do the same chemistry and get to the same product. Both of those would be worth 100% of the credit. Okay? Can anybody tell me anything about these two starting materials? Which one would you prefer to use in the laboratory? The top one? They're the second one. I'm hearing a vote for each. You want the second one? Why do you want the second one? Just no. Yeah, I can get both of them actually. It is easier to handle, but it's not because of stability. Trimethylamine is actually a gas at room temperature, and it smells like rotten fish. Yeah. So this one will work just fine, but don't wear your Sunday best to the lab because you're going to come out stinking that day no matter how good you are with it. This one still stinks, but it's a liquid, a lot easier to handle. Okay? And so there are some practical considerations in terms of which route you would prefer to do practically, but on paper both of them will work equally well, and you would get credit for it. Okay? So we all know that the nitrogen atom of an amine is sp3 hybridized. We have bond angles that are pretty close to tetrahedral. Little compressed from tetrahedral. Why is it a little bit compressed? Lone pairs. And what theory is that y'all learned about in general chemistry? Vesper theory, valence shell electron pair repulsion. And what do we know? We know that a lone pair will repel a bonded pair, right? More or less than another non-bonded pair. Little less. Remember, water has a tighter angle than an amine because there's two lone pairs, right? And those lone pair repulsions are greater than lone pair bonding pair repulsions, right? The reason is because those bonding pairs are between two atoms, okay? So we do have some compression, and we call this overall trigonal pyramidal, okay? And the bond angles are pretty close to tetrahedral, but slightly compressed. Okay. Electronically, it's tetrahedral because we count the lone pair as a substituent, right? But when we look at the atoms, we know that it's trigonal pyramidal. Okay. Now, if we have an amine with 4 different groups attached to it, right? I've got R, R prime, H, and a lone pair. The lone pair is a group. I can make a non-superimposable mirror image of this. And so technically, the amino functional group can be chiral. However, you will not be able to isolate one enantiomer over the other. Can anybody tell me why? We talked about this a little bit when we were in, what was that, chapter 5? Last semester? Pardon?
Can you not do whatever you normally do for temporary separation of that?
You could, but then you're making quaternary ammonium salts, which aren't amines. Quaternary ammonium salts can be isolated as a pair of enantiomers, but amines cannot because of umbrella inversion. Remember that? So that pair of electrons can actually invert, and it inverts like an umbrella, and it does this all the time. It will always exist as a mixture of both enantiomers, okay, if you have an amine. So the nitrogen itself, while technically chiral, you can't resolve one enantiomer over the other when the chirality is at the nitrogen, okay, for these types of groups. And so you undergo what's known as these umbrella inversions. Basically, you're taking one enantiomer going through a planar transition state, which is what? Hybridization. So we're going from sp3 to what? sp2, and that's planar. It's not a carbocation, it's an sp2 hybridized amine with the lone pair in the p orbital, and then that can collapse to the other enantiomer. And this is an interconversion process. You will always have a 50-50 mix of both compounds if the only chiral center you have is on the nitrogen, okay? And so these two mirror images are interconverted quite rapidly. So if you spent a lot of money to try to make the enantiomer on the left, you would just spend a lot of money and have nothing to show for it, because once you've made it, it will rapidly interconvert to a racemic mixture, if you will. Okay, and that's because there's a low barrier to this inversion. There's not much energy required for this to happen. Constantly, yep. Yeah, it continuously goes to that interconversion. Now, there are amines where you can constrain the amine to where the inversion can't happen, and there are examples, but that's beyond what I want to talk about in this class, okay? So technically, yes, you can do it, and I'm telling a little bit of a white lie here, okay? But for all practical purposes, when the R groups are not connected to one another and constrained, the amino groups will interconvert very rapidly, okay? Now, the quaternary ammonium salt's a different story, as Sam was kind of alluding to. Because we no longer have a lone pair, the interconversion cannot occur. Okay, these cannot form an sp2 hybridized transition state, which then interconverts, okay, because there's no lone pair. And so you could prepare quaternary ammonium salts of an amine and resolve those enantiomers through the variety of techniques that we've learned about before. Okay? And so you can have stereogenic centers on nitrogen if they're quaternary ammonium salts. Can't ignore those. Okay? A couple of things about nomenclature. Primary amines can either be named using a systematic or a common name. So for example, if we look at CH3NH2, the systematic name for this is methanamine, methane, minus a hydrogen, right? And then the amine. But the common name, which is what most people refer to this, is methylamine. We typically commonly talk about these as alkyl substituted amines, okay? Not amino substituted hydrocarbons, which is what the systematic name would have us name them. Here, the common name would be cyclohexylamine, or you can use the systematic name cyclohexanamine, okay? Both are fine, but I would almost bet you if you're working a lab, 90% of the time they use the common name here as an alkyl substituted amine, okay? So if I had CH3, CH2, NH2, what would the name be? ethylamine. Or what would the common name be? Or the systematic name, excuse me? Ethanamine. Yep. We also have some aromatic derivatives of amines. These are known as aniline. Okay, so we clearly have an amino group, but it's attached not to just a typical R group, but to an aromatic ring, like a benzene ring. These have special properties because the lone pair of electrons are actually in resonance with the ring, right? Aniline is a very, very useful molecule. Just about every one of you have aniline molecules on you right now in terms of the dyes that are used in your clothes. Okay, they're useful for making dyes. Aniline is also useful for making explosives. Okay, so it's a very useful molecule in general. So aniline is just the benzene ring attached to an NH2. Now we can have other groups attached to the nitrogen as well. So here we have an ethyl group attached to the nitrogen, and so this becomes N-ethyl aniline. What does the N signify? Pardon? So what do you mean by side? It's attached to the nitrogen, that's right. Because if I just said ethyl aniline, that could mean it's attached to the nitrogen of the aniline or it's attached to the benzene ring, right? So we have to be descriptive. And so the way that we tell that we're attaching another group onto the nitrogen of the aniline is by using the N dash. Okay, so actually that's an italicized N, capital, okay? Meaning that on that nitrogen is attached an ethyl group on aniline. If you look at the last molecule there, orthobromoaniline, the nitrogen takes precedent, and so we name it as an aniline group, and the bromine is a substituent on the aniline aromatic ring, and those are in the 1-2 relationship, so that's ortho. We can also have meta-bromoaniline, and we can have para-bromoaniline, right? Now, there are also some heterocycles that are amine derivatives, piperidine and pyrrolidine. Now, these are true amines, right, because these are just simple R groups, right? Piperidine is related to pyridine. How? That's right. So if you take pyridine, you can actually hydrogenate pyridine and get piperidine. Takes a lot of energy to do it, but because it's aromatic, but you can do it. Okay? Pyrrole and pyrrolidine are related by the same relationship, right? And so pyridine and pyrrole are, decent bases, but piperidine and pyrrolidine are actually pretty good bases in themselves. They're both secondary amines. Okay. You're going to find in terms of physical properties that the primary and secondary amines have higher boiling points than similar compounds. So for example, if you look at, what do we have there? Diethyl ether versus propylamine. You'll notice that the boiling points are quite a bit different there, right? And if you look at the alcohol, you'll see that the boiling point of the alcohol is actually quite a bit larger. So the amines are somewhere in between in terms of their ability to form hydrogen bonds. So it has to do with the increasing intermolecular forces. Tertiary amines, however, will typically have lower boiling points than primary and secondary amines of comparable molecular weight. So if you look at this tertiary amine versus this secondary amine, essentially the same molecular weight, you'll see quite a bit of difference in those boiling points, and that has to do with hydrogen bonding with each other. So that secondary amine can form hydrogen bonds fairly easily, whereas the tertiary amine has no hydrogen to hydrogen bond with itself, so you don't have any of that. In terms of solubility, amines are soluble in organic solvents. They follow the 5-carbon rule, so amines that have less than or equal to 5 carbons per nitrogen group are going to be soluble in water. And amines that have greater than that are typically insoluble because you have just so much carbon there. And again, that's just a rough rule of thumb. There are certainly some exceptions to those rules, but that's a good rule of thumb to live by. In terms of your infrared spectra, you can clearly tell the difference between a primary and a secondary amine by the number of peaks that you see in the IR. So in the hydrogen region, a primary amine is going to have 2 peaks somewhere around here, and we call that the amine doublet. A lot of people will call that the amine doublet, primary amine doublet, I should say. Why do I see 2 peaks for the primary amine? There's 2 hydrogens, so what? So why would I see 2? If I look at just a typical amine, right, and I look down that carbon-nitrogen bond, those 2 hydrogens are going to be related by symmetry. So why do I see 2 peaks? Well, but they're symmetrical, so why do I see 2 of them? What are we actually looking at in the IR? Are we looking at the bonds? We're looking at the stretches, right? And so how can I imagine those 2 hydrogens stretching? I can imagine those 2 bonds stretching at the same time in the same direction, or I can imagine one coming in and one going out. So an asymmetric stretch and a symmetric stretch. And that's why I see 2 NH bonds, or vibrations, if you will, for a primary amine, because I can have a symmetric stretch, or I can have an anti-symmetric stretch, and those occur at different frequencies. A secondary amine only has 1 hydrogen, and so you're only going to see 1 peak, the NH. It can only stretch, right? It has no counterpart to counterbalance it, if you will. And then a tertiary amine, you will see no hydrogen in the hydrogen region because it isn't there. Okay, so if you had a series of amines, you can actually use IR to determine whether you have a primary, secondary, or tertiary amine by simple IR analysis. In the NMR, the hydrogen that's attached to the nitrogen quite frequently appears as a broad peak that does not couple to its neighbors. Okay? If you look at this, you would say, well, that CH3 group, that methyl group, has 1 neighbor, so it should appear as a doublet, right? But in fact, it appears as a singlet. And you would think that this, having 4 neighbors, should appear as 3 neighbors should appear as a quartet, but it appears as a broad singlet. What do you remember about hydrogens attached to heteroatoms from the NMR chapter? They don't split, sometimes, actually quite frequently. But why? Not shielding. Shielding is the position on the ppm scale. Because they can hydrogen bond, they can also exchange. That hydrogen doesn't actually belong on that molecule. It can actually be exchanged to another molecule through an exchange process. You can get exchange of the hydrogen occurring because of hydrogen bonding. And since it's being exchanged out very, very rapidly compared to how fast the NMR can actually look at it, it's almost as if it's not on the molecule to be coupled. Now, I can use certain reaction condition, or not reaction, but experimental conditions in the NMR where I will see the coupling, and we see that quite a bit. But for the purposes of this class, don't think of them as being able to couple. They rarely couple. Okay? So the NHs usually appear as these broad peaks, usually somewhere around 4 or something. Let's talk about some interesting and useful amines. Useful is a broad term here. Histamine, for those of you who have allergies this time of the year, right? What do you take? An antihistamine, something like brompheniramine. So if you use a generic version of an antihistamine, look on the back of it, chances are that molecule is the over-the-counter stuff that you're taking. Usually is the hydrobromide salt, so we'll say brompheniramine hydrobromide. This is histamine. This is what's causing all your problems with your allergies right now. And this is what blocks the receptor for this. Okay? How are they related? And how are they different? How is the drug related to the cause of your allergies? Okay, yeah. Does histamine, is it aromatic or non-aromatic? It's not anti-aromatic. You sure? What are the rules for aromaticity? It has to be cyclic, has to be planar, fully conjugated, and has to satisfy what, Sarah? 4n plus 2 Huckel's rule, right? If you look at that, all of those are satisfied with that ring. It is cyclic. It is completely conjugated. Okay, it is planar. If you built a model, you'd see that. 2, 4, 6 electrons in that aromatic ring. Remember that lone pair is in the plane of the aromatic ring, so that they are delocalized. It's an sp2 hybridized nitrogen. Yes, Gabby? Because these are orthogonal to the pi system. So if you built a model, you'd see that this would stick out 90 degrees and your p orbitals would be like this, whereas these electrons are actually in a p orbital. It has to do with, well, if you drew other resonance structures, but these 2 electrons count. So yeah, both of those have aromatic rings. The drug has an aromatic ring. The histamine has an aromatic ring. Both of them have nitrogens in the aromatic ring, right? What else is similar? They both have some type of alkyl group, right? With a nitrogen. What are the differences? Okay, tertiary amine for the drug versus a what kind of amine for the primary amine? And I heard that the drug also has an extra aromatic ring. So the drug can actually get into the receptor, block it to keep the histamine out. And the drug doesn't elicit the response that histamine does. So it's a way to help out with your allergies during this allergy season. Tagamet, this is an anti-ulcer drug. Notice all the nitrogen that's contained in that molecule. Okay, so if you have ulcers and you take Tagamet, that's the active ingredient. What other functional groups do you see in Tagamet? Yeah, there's sulfide in there, right? So the thioether, if you will, the sulfide, also present in that particular molecule. Some other interesting amines, one up top, the one that most of us are addicted to, caffeine, right? It is an aromatic amine. It is actually quite bitter, can result in insomnia, stimulates the secretion of stomach acid, gives you that feeling of alertness. What do you think about its toxicity? Yeah. It's actually quite toxic. You just don't have that much caffeine in the drinks that you're drinking, okay? If I was to give you pure caffeine, it'd be pretty easy to kill you. I think it's about 1/4 of a teaspoon of pure caffeine is a lethal dose. The thing is that you will drink it and drink it and drink it, but you will process it faster than you can consume it. You just can't consume. You literally have to drown yourself in coffee to have that kind of. So caffeine is actually quite toxic. Nicotine, right? The tobacco plant. We know that it's addictive and it is highly toxic. Okay. There is a story, I've never verified if it's true, so you might want to do a little research to see if it's true, but I had a professor once tell me that during World War II, spies always carried with them to cigars, because if they got caught, they would eat the cigars and it would be suicide. It's how they killed themselves, and nobody would deny somebody their smoke, so to speak. So it was one way in which people offed themselves if they were captured by the enemy, because nicotine is extremely toxic. Okay. Which? Nicotine. Nicotine can actually be absorbed through the skin. That's why they have Nicoderm patches. So people that are trying to go through smoking cessation type programs, right? So basically that slow release nicotine to help them with their withdrawal symptoms. What else can you tell me about nicotine? Is it chiral or is it achiral? It is chiral. Where's the chiral center? It's on the 5-membered ring, right? Right there. And in fact, it turns out that this structure is actually useful pharmaceutically. And so there are a number of people that are studying ways in which they can increase the nicotine content of tobacco so that you can industrially remove the nicotine and use it for other reactions, not just for smoking. Okay, so there is a lot of research that's going on at tobacco companies as well as in academia to try to figure out how to make better use of nicotine for a variety of drug manufacturing processes. It's chiral, it contains the chiral center. It's an amine, which is it contains a 5-membered ring, which is also important for a number of pharmaceuticals, and it contains a pyridine ring. So there's a lot of interesting molecular structure in this simple molecule. And so as fewer and fewer people smoke in the United States, tobacco companies are trying to find other uses for their product that don't involve you having to smoke. So nicotine actually is industrially prepared from the tobacco plant and utilized for a variety of things. And it is actually utilized as a commercial insecticide. You can spray this on other things to kill a variety of insects, because that's why the tobacco plant makes it, to kill their predators. Conine, this is the stuff that Socrates drank. So is it poisonous? It's extremely poisonous. So what is the theme of amines? They're toxic. That's right. They belong to a class of molecules known as alkaloids, and most alkaloids are quite toxic. Okay? So especially primary amines and secondary amines are quite toxic. Okay? And so you basically take hemlock roots and you boil it up into a tea, and it contains a significant amount of that. What kind of amine is that? Primary, secondary, or tertiary? It's a secondary amine, and it is chiral. Notice that the carbon just to the right of the nitrogen there is a chiral center, and the plant makes one and only one enantiomer. Okay. Another example, this is dopamine. This is a neurotransmitter. It's a primary amine. Now wait a second, I thought I just said that primary amines were toxic, right? And they are, but they're also useful. So it's a neurotransmitter. Dopamine can kill you, but your body releases dopamine in very low concentrations on demand when needed. It does not store it as dopamine. It stores it as a precursor, which is then synthesized into dopamine as needed to do the neurotransmission, nerve impulse. I don't understand all the brain stuff of it, okay, but you can study that in other classes. But basically, dopamine will cross this channel, and that's how a nerve impulse is released. And so dopamine under physiological pH is actually charged, and it carries the electrical impulse, basically. Okay? So these amines are quite useful. Now, the preparation of amines is somewhat of a challenge. Practically, if you look at it, you should just be able to take ammonia. That's what amines are. They're just derivatives of ammonia, NH3. And you should just be able to take ammonia and react it with an alkyl halide and make a primary amine. Right? So if you take ammonia and you react it with, just some alkyl halide, let's say methyl bromide, You'll get an SN2 reaction, which gives you a quaternary ammonium salt. This hydrogen is acidic. It reacts with the extra ammonia that you have present, and you'll get an ammonium salt. In this case, it'd be ammonium bromide, and you'd get a primary amine. On paper, that looks really nice and convenient, but there's a problem, and that is that the primary amine is actually more reactive than the ammonia in terms of an SN2 reaction. Why is that? Why would a primary amine be more reactive than ammonia in an SN2 reaction? That's right, and so it makes that lone pair more basic or more nucleophilic, right? And so now the primary amine, once it's generated, is more reactive, so it will react with the remaining alkyl halide to make a secondary amine, which, what do you think? More reactive than the primary amine, which it goes on and reacts to make a tertiary amine, which is still reactive and will react with excess alkyl halide to make the quaternary ammonium salt. If you want to make a quaternary ammonium salt, this is what you do. You take the alkyl halide in excess and you throw in ammonia. Voila, you get a quaternary ammonium salt, and quaternary ammonium salts are used as antibacterials in your hand soap. That's how they make them, okay? And that works really, really well. But what if you want to make a primary amine? We need new synthetic technology to do that. What if we only want to make a secondary amine? We need some other way to do that. If we want to make a tertiary amine, you all have already proven how you can do this in the lab. What reaction did you all use? You used the Eschweiler-Clark reaction, right? You've already talked about that. I'm not going to talk about that in here. You already know it. What was the Eschweiler-Clark? Formic acid and formaldehyde reacting with what kind of an amine? A primary amine. And so what kind of groups did you put on that primary amine? 2 methyl groups. The Eschweiler-Clark only puts methyl groups on. And it stops at the tertiary amine. So if I want to make a tertiary amine where 2 of the R groups are methyl groups, the Eschweiler-Clark's the way to go. You just take your primary amine, your formaldehyde solution, and away you go. We can make quaternary amines with, starting with tertiary amines and reacting with alkyl halides. We've just talked about that on the board. You can actually make primary amines from ammonia and an alkyl halide if you use the ammonia in huge excess, right? Because we know an SN2 reaction is dependent on the concentration of the nucleophile and the electrophile, right? Well, the nucleophile being the primary amine in the product, if we keep its concentration really, really low relative to ammonia, its rate will be slow, right? We can play some math here. What do you think we need in terms of an excess of ammonia to get this to work? Yeah, give me a number. 4 to 1? Not even close. It's like a swimming pool to a Coke bottles ratio. You need a huge amount of ammonia to get that reaction to be practical, okay? And so do you think that's practical? Not really. It's not particularly useful. You got to have way more ammonia than you have your alkyl halide to have it stop at the primary amine, okay? So we can play those games, but they're not particularly useful. And so there's another way that we can make primary amines very, very selectively, very, very practically, using the Gabriel synthesis, okay? So it turns out that phthalimide has a pKa of about 10. That hydrogen is fairly acidic. Why is that hydrogen fairly acidic? Yeah, the 2 carbonyls, right? These 2 carbonyls are electron withdrawing. Makes this hydrogen particularly acidic. You can actually take phthalimide, react it with potassium hydroxide or sodium hydroxide, doesn't matter. You get the phthalimide anion, which then is resonance stabilized, and that's why the pKa is so low. Or you can just buy a bottle of potassium phthalimide, which is what we do in our lab. We do a lot of Gabriel synthesis in our laboratory, okay? It turns out that that nitrogen is a pretty good nucleophile. and it will react with alkyl halides to make a new carbon-nitrogen bond. And it stops there. Why doesn't it react a second time? Nitrogen still has a lone pair on it. Maggie, why do you suppose that the product that we get here doesn't continue to react with the alkyl halide to put another carbon group here? There's a lone pair on that nitrogen, but why doesn't it react? Steric hindrance? It's not steric hindrance here. Resonance. That lone pair is actually delocalized across those two carbonyls, right? So if it's not steric hindrance, it's got to be resonance, right? Or pKa. Or pKa. Right. Or use a Grignard. Yeah, don't use a Grignard every time you need to do something. So it stops there. And we formed a single carbon-nitrogen bond, which is what we need. That's what a primary amine is. So what do we have to do? We have to remove all of this. This is nothing more than a protecting group. And there are 3 ways in which we can remove that. We can remove it under basic conditions. We can take the Gabriel product, boil it up in aqueous sodium hydroxide or potassium hydroxide, and we'll get the primary amine. We can boil it up in acid and do the same thing, except we won't get the primary amine, we'll get the ammonium salt of the amine. Or we can treat it with hydrazine, NH2NH2. And that selectively deprotects the phthalimide over other groups. And that's actually the chemistry that we use in my group all the time, is the hydrazine deprotection of a phthalimide. Okay? But there are 3 ways in which we can deprotect the product of the Gabriel synthesis. Okay? Basic, acidic, and then hydrazine treatment. All 3 of them will work just fine to ultimately give you the primary amine. Okay? We can also synthesize amines from nitro compounds. So if we have a nitro group on a whatever, an alkyl group or an aromatic group, we can reduce that by a variety of conditions to give us a primary amine. Okay? Tell me something about those conditions. Which one would you use if you came into my laboratory? Let's say we had a nitro compound and we wanted to get the primary amine. Which one of those conditions would you use? Would you use catalytic hydrogenation, or would you use iron and HCl or tin and HCl? Either one. Why? It's cheap. That's right. Palladium is not a cheap metal, right? So we can actually make these compounds by reduction of nitro groups. So how then would you take benzene and make aniline out of it? How would you do that chemistry? Okay, tell me. What would you take? You'd take benzene and react it with what? Nope. What would we have to put on first? Nitro. So how do we nitrate benzene? A mixture of nitric and sulfuric acids, right? We'd go through electrophilic aromatic substitution, would put a nitro group on, okay? And then Sarah would take the nitrobenzene and she would do what with it? She would reduce it to the aniline using iron and HCl, tin or HCl, or catalytic hydrogenation if that's the only way she had to do it, okay? Those reactions work very, very well. We can also make primary amines from nitriles using our good friend LAH. Sodium borohydride will not do this. Catalytic hydrogenation will not reduce this effectively. So we have to use a strong reducing agent like lithium aluminum hydride. Okay? Notice it's stepwise. First the lithium aluminum hydride, then the water. not together, right? Not together. And so we can ultimately take alkyl halides and make amines then through this process. So let's say we have iodomethane and we want to get ethylamine. How can I do that? I need a couple steps. How can I do that? Nope. If I did the Gabriel synthesis, I would just have a methyl group on the nitrogen, not an ethyl group. So what do I have to add? What's the difference between iodomethane and ethylamine? I need another carbon, don't I? Well, so what I would do is I would take iodomethane and I would first react it with sodium cyanide, which would give me the nitrile, right? And then reduce that with LAH. So I can take an alkyl halide and add a carbon and a nitrogen by going through the nitrile functional group. And we know that cyanide's a pretty darn good nucleophile, and it works quite well here. Okay. We can also make amines by the reduction of amides. I can take a primary amide and I can reduce it to a primary amine. All I got to do is remove the two carbon-oxygen bonds and replace them with carbon-hydrogen bonds. Turns out lithium aluminum hydride will do that just fine. I can take secondary amines and make secondary amides, and make secondary amines. And I can take tertiary amides and make tertiary amines very, very selectively by these lithium aluminum hydride reductions. For your information, you don't have to just use lithium aluminum hydride for these reductions. You can also use borane. Where else have we used borane before? BH3. Hydroboration oxidation. It's a reducing agent. It will also reduce primary, secondary, and tertiary amides into the respective primary, secondary, and tertiary amines. It is the reagent of choice in my laboratory because we don't like working with lithium aluminum hydride for obvious reasons. Borane is a liquid in solution. We can syringe it out very easily. We don't have to worry about it being explosive with water. Kind of nice. Okay. So that finishes that up for today. We are going to have, I sent out a thing by Remind about tomorrow evening. I'll buy pizza. I think it'll be in this room, but I haven't heard back from Carla yet. I'll send that out by Remind, and I'll also capture that and post it to YouTube if you can't be here. I understand. Feel free to bring anything you want. And go ahead and turn in your inverted lecture, and I will see you on tomorrow night or Wednesday.